Good afternoon, madam. Can you hear me? Pratima Panigar, madam.
Yeah, I can hear you, madam. Good afternoon.
How are you, madam?
Yeah, I am fine. How about you people?
Yeah, we are all fine, madam.
Okay.
Just we will start at 3, madam, sharp, so that the participants will be joining, madam.
Yeah, sure. Just I was trying whether I'll able to join or not. That's why. No problem.
Okay, madam.
Yeah.
Okay, madam. Okay, thank you.
శ్వేత మ్యామ్ నా వాయిస్ వినిపిస్తుందా?
Yes, Monica, you are audible.
Okay, thank you.
Good afternoon, everyone. I welcome you to this third day of 1 week online National FDP on fundamental mathematics, the second session. This program basically celebrates birth anniversary of Mariam Mirza Khani, the only woman field medalist till today. To achieve what you have not, you must become what you are not. You have to grow into your goals. I once again welcome you for this third day, second session of this National FDP on fundamental mathematics. Now I call upon Monica to introduce today's speaker, Professor Pratima Panigrahi Madam.
Yes, ma'am. Ma'am, am I audible? It is one voice.
Yes, you are audible, Monica.
Shall I continue, ma'am?
Yes, you can continue.
Good afternoon, one and all. I'm Monica, Assistant Professor, Department of Mathematics and Statistics, RBBR Women's College. It's my privilege to introduce today's speaker, Pratima Panigrahi ma'am. Ma'am has completed her PhD from Indian Statistical Institute, Bangalore, and pursued MSc Mathematics from Sambalpur University. Ma'am was awarded gold medal for securing first rank in MSc Mathematics from Sambalpur University. Ma'am received fellowship from National Board of Higher Mathematics for doctoral, postdoctoral research, and merit scholarship for securing third rank in BSc Mathematical Commerce. Ma'am has 20 years of experience in teaching and research at IIT Kharagpur. Ma'am has guided 13 PhD students and published papers in peer-reviewed journals. Ma'am has organized a national workshop sponsored by DST on some recent research directions in graph theory in the Department of Mathematics, IIT Kharagpur, during 26th May to 30th May 2008. Ma'am has published around 71 papers at national and international level. Ma'am has attended many conferences and presented papers also. Ma'am has taken many institute responsibilities, and currently Ma'am is in charge of physically disabled students. Ma'am, you are very much inspiration to one and all. Thank you, ma'am, for accepting to be a speaker for today's session. Now I request ma'am to take over the session. Thank you, ma'am.
Thank you, Monica madam, for introducing me. And also I am thankful to Sweta madam and Uma madam for inviting me to deliver a lecture in this prestigious workshop. Well, so I shall share my slides for presentation. Okay. Okay, I'm trying to find out to share because I am not used to Zoom platform so much. I do use MS Team, so I'm
Madam, at the bottom side, you will be having share screen, madam.
Yeah, share is there. So
yeah, you can click that.
I'll click that. Then where is my slides? Where I can go? I haven't selected. I think before that I should select.
Download it, madam. First of all, you have to download it.
Yeah, I have downloaded.
Yes.
It is already there. Okay, once again, I'll start sharing. Actually, where I am not able to find out my just 1 second. I have already downloaded and it is on my desktop. So where I should go for presentation?
Madam, already as you have downloaded, you can share the screen and then from as you can minimize that.
Okay, by minimize the screen, then it will share.
At the top, you will be finding the downloaded ones, no, madam? Yeah. Madam, you can see your desktop, madam. Desktop view.
Yeah, desktop.
Yeah.
Okay, so now it is sharing, okay?
Yes, madam.
Okay, okay, thank you so much.
You're welcome.
Well, all of you can see my slides, right?
Yes, madam, we can see your slides.
Yeah, okay. Okay, without wasting any time, let us come to the topic. And today my topic of my lecture is this on graphs constructed from algebraic structures and their different kind of spectra. Well, so in this title, we can see that there are three kind of topics are involved. That first topic is graphs. And second topic, algebraic structures. So I think you all are, acquainted with these algebraic structures. Algebraic structures means basically here I shall concentrate on groups and rings. There are many other algebraic structures also. And all of you are familiar with groups and rings, so I need not introduce them. And the third topic is spectra. Spectra is actually plural form of spectrum. Spectrum, what is the meaning of spectrum again? So spectrum means that is set of all eigenvalues of a matrix. Set of all eigenvalues of a matrix. That is, we do count their multiplicities also with counting multiplicity. The set of all eigenvalues of a matrix is called spectrum of that matrix. So this is therefore comes from linear algebra, the spectrum topic that we find in linear algebra. So here in this lecture actually, I shall try to link all three topics, that graphs, algebraic structure, the groups, rings, and spectrum of matrices. So we shall link all these three topics and we shall see how we can do it and how we can proceed. Some noise is coming.
Dear participants, I request you to mute yourselves.
Well, since we all, you all are acquainted with these groups and rings, this is a very basic topic. And graphs, I think some of you, it may not be familiar. That is why very quickly I'll tell you, what do we mean by a graph here? There are different kind of graphs also. So we shall consider only simple graphs in this talk. So what do you mean by a simple graph? A simple graph that we denote by this G is a pair basically that B and B, E consist of this pair B and E. B is a non-empty set and E is collection of unordered pairs of elements in B. Here we take the elements of E as unordered pairs of elements in B. In general, actually, this E maybe consist of order pairs or singleton sets, or this may be a multi-set also. But here we consider this simple graph. I'm not going into all detail about different kind of graphs and all. I will just concentrate on simple graph. So a simple graph, in case of simple graph, E is consist of unordered pairs of elements in B only, and this is it. So elements of B are called vertices, we shall say vertices, and elements of E we shall refer as edges. So an edge in this graph means that is basically pair of an order pair of vertices, an unordered pair of vertices in B. I think you understand. I'll give you also example. So whenever it is like this L is an edge, it is consist of unordered pair of elements in V. This X and Y are vertices in the graph, and whenever this pair is an edge, then we say that X and Y are adjacent, otherwise they are not non-adjacent. Whenever this unordered pair XY will belong to this set E, then we shall say that X and Y are adjacent. And other way we can say also, whenever this L is consisting of this edge, L is an edge consisting of this unordered pair of vertices X and Y, then we say that L is incident on these vertices X and Y. Or we can say that this X and Y are called end vertices of this particular edge, or we say that this edge L is incident on the vertices X and Y. So look at here, I have drawn some graphs here, example of graphs. So here this one, just you look at here, it is consist of 6 vertices are there, and here I have made adjacent like this. The vertices I have put in a linear form kind of thing, and then I have made adjacent vertices in this fashion. So this starting vertex and this ending one, look at, they are not adjacent. Okay, they are not adjacent. They are non-adjacent vertices. Okay, so here, in fact, these such kind of graphs are also called paths. So look at this figure here. There are some isolated vertices. In a graph, one can have isolated vertices also. So those, vertices, they are not adjacent with any other vertices. They are called isolated vertices. So in this graph, in fact, we can see that this is a disconnected graph. I'm not coming to all those terminologies, but simply I am referring those connectivity in a graph and all. And this third graph I have drawn here, you see every pair of vertices are adjacent. So this such kind of graphs will be called a complete graph. So this is one example of a complete graph on 4 vertices. A complete graph means that is basically a simple graph, and every pair of vertices are adjacent. You take any vertex that is adjacent to all the 3 remaining vertices. So this is a complete graph on 4 vertices, or this is also called K4 actually. I'll come to the notation. Well, here we shall discuss about finite graph. So what do you mean by a finite graph? Finite graph means both vertex set as well as edge set have to be finite sets. Both are finite sets. Then we shall say that is a finite graph. So in the example, whatever graphs I have drawn are all example of finite graphs. So now, since we are dealing with this concept of finite graphs, so what about infinite graph? Just I want to give one example of an infinite graph. Look at these graphs, are very important. Topic nowadays. It has application in almost all the areas of, science, technology, sociology. See, in daily, day-to-day life, we can come across several kind of graphs. See, this computer network. This is also a graph. Look at, if we consider all the participants of this lecture, as a vertex set, every participant will be considered as a vertex. And if 2 participants, they are friend of each other, then we'll make them adjacent. They will form an edge in the graph. So this will be one example of a finite graph. Okay, this will be an example of a finite graph, because if there are finite number of course, finite number of participants are there. Well, what about an example of an infinite graph? Here I can give one example like this. You just consider that our vertex set V is equal to all the points on the plane R2. All the points on the plane R2. I shall take that as vertex set. So there are infinite number of points on this on this plane. So what about edge set? Unless we define both the sets, what is B and what is E, the graph is not defined. So I have told you that vertex set B only now. So what about the edge set? What about the edge set? Here I am taking vertex set as the set of all the points on the plane R2. Then I shall suppose I can make adjacent, adjacency rule several ways I can give, but I'll give one here. I'll say that 2 vertices are adjacent in this graph if distance between them is equal to say 1. Okay, just I'll say the distance between them is equal to 1. That means how I have constructed this graph, I have taken the vertices edge set of all the points on R2, and 2 points on R2 will make adjacent or will join them by an edge if distance between them is equal to say 1. So definitely this forms an infinite graph. So there are several kind of graphs, several kind of graphs are available, one can construct. So we'll not go to that. We shall concentrate on that graphs related to algebraic structures. So I have already told you about complete graph. Okay, complete graph on n number of vertices, we shall denote by kn. And then next we shall also, talk about complement of a graph. Complement of a graph is denoted by G bar, and G bar is again a graph, and that has the vertex set same as the graph G. Vertex set of G is same as the vertex set of G bar. And what about adjacency? Adjacency in G bar, we are just flipping the adjacency in G actually and getting the its complement. That means flipping means what? In the graph G bar, vertices are same as the graph G, and two vertices will be adjacent in the complement graph G bar if they are non-adjacent in G. If and only if they are non-adjacent in G. Vertices which were adjacent in G will make them non-adjacent in G bar, and vertices which were non-adjacent in G we shall make adjacent in G bar. And also we talk of a null graph. Null graph means H set will be empty. H set will be empty means it will not contain any edge, or in other words, it is exactly the complement of a complete graph. Well, there are some, that are some other terminologies and all, and that I may discuss whenever we come across in this lecture. So within this short period, it is not possible to, that explain about all the terminologies, all graph terminologies. So let us come, quickly come to some matrices associated with graphs. So how matrices can be, attached to graphs? How can we define matrices from some graphs? Well, the most popular matrix associated with a graph is the adjacency matrix of the graph. Adjacency matrix of the graph, G we denote by AG, A of G, and its entries are Aij are actually basically either 1 or 0 only. When the rows and columns of this matrix, adjacency matrix, will be rows and columns will be indexed by vertices of the graph, and whenever two vertices are adjacent, their corresponding entry in this matrix will be 1, otherwise 0. Whenever two vertices are non-adjacent, their corresponding entry will be 0. So this is basically a 1-0 matrix. We are considering the graph to be simple graph, so therefore the entries will come to be 1 or 0. So this adjacency matrix is very important matrix associated with a graph, because that we can implement this graph theoretic problems in a computer by taking help of this adjacency matrix of a graph. See, we want to perform certain operations on graphs, and those may not be done by hand kind of thing, and take help of a computer. So how can we do? How can we represent a graph in a machine, in a computer? So quite often we take help of this adjacency matrix of a graph to represent a graph in a computer. Well, another popular matrix is this Laplacian matrix associated with a graph. So whether it is all right that you can understand what I'm saying. If you don't understand at some point, then you can always, ask me. You are free to interrupt and clarify your doubts if you have any query. Well, so the next, the next matrix associated with a graph G is the Laplacian matrix. Laplacian matrix is defined like this. Laplacian matrix LG is actually equal to this diagonal matrix associated with the graph G minus adjacency matrix of the graph. So what is this diagonal matrix associated with the graph G? Actually, D is a diagonal matrix, and the diagonal entries are degree of vertices in the graph G. So degree of vertices in the graph G. So what do you mean by degree of vertices in a graph G? Okay, let us come to this example of graphs that I have considered here. So look at this path. This is a path graph. So the degree of, in case of simple graph, degree of a vertex is the number of edges incident on that vertex. In case of a simple graph, the degree of a vertex is the number of edges incident on that vertex. So here you just look at on this first vertex, only one edge is incident on this vertex. So degree of this vertex is equal to 1. Then the second vertex is degree 2, third, fourth, fifth have all degree equal to 2. And this last one is having degree, degree 1. And in case of this complete graph K4, degree of every vertex is equal to 3. So we understand that, the meaning of degree of a vertex. So degree, this is how that degree diagonal matrix of a graph G we form, that we denote by DG. This is a diagonal matrix. Diagonal entries are degree of the vertices of the graph G, and all other entries are 0 because this is a diagonal matrix. And the Laplacian matrix is formed like this, that the diagonal matrix minus the adjacency matrix, or in other words, I'll come to one example quickly that we can see here. So look at this graph I have considered. In this graph, say this is H. The vertices I have taken are B1, B2, B3, B4, and B5. You look at first of all, this adjacency matrix of this graph H. Adjacency matrix of this graph H, since we are considering simple graph, no vertex will be adjacent to itself. So all diagonal entries will be equal to 0 for adjacency matrix. And here actually the rows are indexed by the vertices B1, B2, B3, B4, B5. Similarly, the columns also in the same order we have to index B1, B2, B3, B4, B5. See, the first entry B1, B1, obviously they are not adjacent, so therefore 0. Then B1 is adjacent to second vertex, the B2. Therefore, this entry B1 is adjacent to B2, therefore we get 1. And this here this B1 is adjacent to B5 also. You look at in this graph, B1 is adjacent to B5, therefore this entry is 1, and all other entries are 0 because B1 is not adjacent to it, B3 and B4. Similarly, we form this adjacency matrix of this graph H. And here is this diagonal matrix associated with this graph H, that is DH. So here this first diagonal entry is the degree of vertex B1, that is 2, and that degree of B2 is second diagonal entry, that is 3. Degree of B3, B4 both are equal to 2, and degree of B5 is 3. This is how we get diagonal matrix. So therefore the Laplacian matrix associated with this graph will be like this, that is DH minus AH, right? DH minus AH. So therefore we get the diagonal entries will be like this, and the other entries will be that whenever the one was there, minus 1 actually, minus AH was there. So this is what the Laplacian matrix associated with this graph. This Laplacian matrix is also very important in graph theory actually, graph theory and combinatorics. This Laplacian matrix, using Laplacian matrix, one can get several properties for graphs. In fact, there is the famous matrix tree theorem, which tells that, about the number of spanning tree in a connected graph. It gives number of spanning tree in a connected graph. That actually comes in terms of that minors of Laplacian matrix of the graph. And I mean, this is also very important, therefore. Well, I have told you that we'll try to relate these three topics, that graphs, groups, rings, that is abstract algebra and linear algebra. So already we have constructed some graphs associated with, constructed some matrices associated with graphs, right? We have already constructed some matrices associated with graphs. Well, there are several type of matrices associated with a graph. In the literature you can find, actually here just I shall name few of them. So here we defined, I mean, there are other kind of matrices also associated with graphs. They are called signless Laplacian, Seidel matrices, Seidel matrix, generalized adjacency matrix of a graph are also defined. And to define these matrices, Seidel and generalized adjacency matrix of a graph, we take these notations, that is the identity matrix IN, and this Jn is all one matrix. I mean, all the entries of Jn are equal to 1. So signless Laplacian matrix, that is Qg, that is equal to dg plus ag. In case of Laplacian, it was dg minus ag. And signless Laplacian, if we take this plus only, this is the difference between Laplacian and signless Laplacian. And then Seidel matrix is defined like this: Jn minus In minus twice adjacency matrix of the graph. And this generalized adjacency matrix is, this is basically the linear combination of adjacency matrix, identity matrix, and this all one matrix Jn. Here x, y, z are actually real numbers and x is not equal to 0. I mean, here we get this is called generalized adjacency matrix, because we can get from this AG, this generalized adjacency matrix, we can derive adjacency matrix also by taking this x equal to 1 and y and z equal to 0. Then in that case, this generalized adjacency matrix will agree with the adjacency matrix. Well, so recently, actually, another important kind of matrix has been given by Hammers and Omidi, and that is called universal adjacency matrix of a graph G. So universal adjacency matrix is again more general than the generalized adjacency matrix. Well, what is the universal adjacency matrix of a graph G then? It is linear combination of adjacency matrix of graph G, and this degree diagonal matrix DG, and this identity matrix IN, and all one matrix JN. Here alpha, beta, gamma, and eta, they are real numbers, and alpha, of course, we take that is not equal to 0. See, by substituting the values of alpha, beta, gamma, and eta suitably, we can obtain from this universal adjacency matrix, we can get adjacency matrix, we can get Laplacian matrix, we can get signless Laplacian matrix, we can get Seidel matrix, and also generalized adjacency matrix also. All the matrices what we have discussed here, that we can put together and form this universal adjacency matrix. So if, I mean, or in other words, this universal adjacency matrix actually that is, I mean, that provides a tool to explore all these adjacency Laplacian, Seidel, signless Laplacian, and generalized adjacency matrix collectively. Well, so there are many other graphs also, but many other matrices associated with graphs. I am not coming to them. So let us come to this spectrum. I have already told you that meaning of spectrum, but still, let us see in proper way that definition. So for a square matrix M of order n, you all know that the characteristic polynomial of M, that is a notation we use as phi m lambda, and that is, determinant of m minus lambda I, and this is the characteristic polynomial. And spectrum of M is the multiset of all eigenvalues of M. So why do I take multiset here? Multiset, what is the meaning of multiset? Multiset means some elements may repeat or repetition of elements will be taken into account. So that is called multi-set. So I mean, if there is a repeated eigenvalue, say some lambda 1 repeating 5 times, then in this spectrum that will appear 5 times. Its multiplicity 5 will be taken into account. So this is called spectrum of a matrix, square matrix M. And you know that from this graph, actually, we have already defined some matrices. Already we are having the matrices. So now we shall find out eigenvalues and eigenvectors of these matrices. And eigenvalues and eigenvectors of AG is adjacency matrix, are called simply eigenvalues, because this is a very popular matrix. So eigenvalues or eigenvectors, and sometimes people do refer as adjacency eigenvalues and adjacency eigenvectors of the graph G. So adjacency eigenvalues and eigenvectors of graph G means actually we mean eigenvalues and eigenvectors of adjacency matrix of the graph G. So similarly, we will have this Laplacian eigenvalues, eigenvectors, signless Laplacian eigenvalues, eigenvectors, like this. And for universal adjacency, universal adjacency eigenvalues, eigenvectors means they are eigenvalues and eigenvectors of this universal adjacency matrix of graph G, this UG. Well, since this adjacency and Laplacian matrices are very popular matrices, quickly we can have some well-known properties of these eigenvalues, adjacency eigenvalues and Laplacian eigenvalues. In fact, why do you study this, a spectrum of adjacency matrix and Laplacian matrix of a graph? So what for we find out eigenvalues, eigenvectors of these matrices? Actually, they are very important, important problem actually. From those eigenvalues, we can determine some some parameters or some properties of graph also that we can extract. So here this theorem gives some properties of that sort, that what information we can get from eigenvalues, from adjacency eigenvalues of a graph. So here I have considered G is a graph with adjacency eigenvalues lambda 1, lambda 2 to lambda n. Then first property is that sum of all the adjacency eigenvalues of graph G is equal to 0. Actually, it comes from that, property we are having, that sum of all eigenvalues of a matrix is equal to trace of the matrix. And here, just you recall that trace of adjacency eigenvalue, adjacency matrix of graph G is equal to 0, because all the diagonal entries of adjacency matrix of graph G are equal to 0, therefore trace is 0. It comes from there. And the next property is very interesting. If we take the sum of square of these eigenvalues, then that gives you that sum of degree of all the vortices. Di are the degree of the vortices. Sum of degree of vortices of the graph. And from the first theorem of graph theory, actually we know this result, that sum of degree of all the vortices is equal to twice total number of edges. So therefore, from the eigenvalues, adjacency eigenvalues, we can tell about the total number of edges of the graph. And another important property is that if G is a bipartite graph, G is a bipartite graph. Bipartite graph means basically if we can partition the vertex set of the graph into two parts, say V1 and V2. That vertex set we partition into two parts, V1 and V2. And no two vertices within V1 or V2 will be adjacent, and vertices within the part will only be adjacent. I'll give also some example later on, example of bipartite graph. So if G is a bipartite graph, then the eigenvalues are symmetric around 0 kind of thing. That is, Whenever lambda is an eigenvalue of graph G, then minus lambda is also an eigenvalue of graph G with the same multiplicity. So therefore, I mean, from this spectrum, adjacency spectrum of a graph, we can say that whether the graph is bipartite or not also. This is another important property. Similarly, for Laplacian eigenvalues of a graph G, if we consider that some properties, some well-known properties we shall, I mean, list here. So, I mean, all the Laplacian eigenvalues of graph G are non-negative. They are zero or positive. And zero, of course, zero is always a Laplacian eigenvalue of graph G with corresponding eigenvector will be equal to 1, 1, 1. I mean, looking at the Laplacian matrix, we will able to determine this. 1, 1 is always an eigenvector because you see, in case of that Laplacian matrix of a graph, the sum of all the entries in any row you take, sum of all the entries in any row you take, that is equal to 0, right? So therefore, from there we get that 0 is a Laplacian eigenvalue with corresponding eigenvector all 1, actually, all 1. And here this is third property is very interesting one, that multiplicity of 0 is always an eigenvalue, and that multiplicity of 0 will be number of connected components of G. The multiplicity of 0 will tell you whether the graph is connected or not. If multiplicity of 0 is 1, then it is connected graph, otherwise not. And also this, I mean, if we take the sum of all Laplacian eigenvalues, say mu I, that again gives you, that is the sum of degree of all the vertices, that is equal to twice total number of edges. So Laplacian spectrum of a graph also gives idea about the total number of edges in a graph. Okay, that's what I have written here. I mean, that the spectrum of adjacency matrix of a graph can determine number of edges, and also it can determine whether the graph is bipartite or not. But this adjacency spectrum cannot determine about the connectivity or connectedness of the graph, whether the graph is connected graph or not. But this Laplacian matrix actually, it can determine, I mean, it can determine total number of edges. Also, the graph is connected or not, it can tell, right? So therefore, but this Laplacian spectrum cannot determine that graph is bipartite graph or not. So therefore, different kind of spectrum of a graph gives different kind of information about the graph. Okay, so I mean, all these spectra are therefore important to extract properties about graphs. Well, so now we shall come to the algebraic structures. So we are having actually how can we form these groups of graphs, from groups, actually we shall consider, we are having groups. From groups to graphs we shall move. Okay, we shall link, we are having algebraic structure, some groups and rings. From groups we shall construct graph, and from graph then we shall move to the spectrum. This is what that this connection, or this this link between these three topics. From we shall start with algebraic structures, from there we shall construct graphs, and from graphs we shall find out matrices, and from matrices we shall find out the spectrum. Okay, so the most popular class of graphs obtained from groups are the Cayley graphs. Cayley graphs had been obtained in 1878 by British mathematician Arthur Cayley. So Cayley graphs are very symmetric, highly symmetric graphs, and that is why they have application in several areas of science, in physics, also to study this quantum works, and all people do use the Cayley graphs, and in computer science also to design interconnection networks. Cayley graphs play important role. And then after that, I am not going much into this Cayley graphs. So after that, actually, a bit recently, that graphs constructed out of some groups are power graphs. commuting graphs, non-commuting graphs are few of them. So I shall, just tell you what are these graphs quickly. I shall discuss mainly Cayley graphs and power graphs associated with a group. So what do you mean by a Cayley graph associated with a graph? So to define a Cayley graph, we take a finite group. Here G we are taking a finite group, and S we are taking a non-empty set. S is a non-empty set, and S does not contain the identity element of the group, and S will satisfy this property. I mean, whenever any element S is there in the set S inverse will also be there in the same set. We shall select such kind of subset S. Then the Cayley graph we shall denote with respect to this. I mean, we can say this set S, GS. If we change this set S, this connecting set, we can say that S if we change, then the graph will also change. We'll get different Cayley graph. It depends on this set S we are choosing. So here the vertex set of this Cayley graph is the set of all the elements of this group G, and two vertices will be adjacent G and H. Whenever this GH inverse will be in S, belongs to S, then G and H are adjacent. So let us quickly see one. See one example. Here I am taking this finite group Z5. Okay, that is integers modulo 5. 0, 1, 2, 3, 4, 5. Operation is addition modulo 5. So in this figure, that therefore the vertices are 0, 1, 2, 3, 4, 5. Okay, and I am taking this set S as 2, 3. 2, 3 S should satisfy that. I mean, whenever an element S belongs to this set, its inverse should also be there. So additive inverse, here operation is addition modulo 5. So 2 and 3, they are inverse of each other, right? Addition modulo 5. And here we can see that this 1 will be adjacent to 4 because 1 plus 4 is equal to 5. Okay, and therefore this 1 plus, okay, here I have taken, there is some notation problem, I think, here. Oh, okay, GH inverse. Okay, fine. Now it is all right. GH inverse. You have to take this operation. G is 1 and H inverse. H is 4. Inverse of 4 is equal to what? Inverse of 4 is equal to 1. So now you have to add 1 and inverse of 4 is also 1. So 1 plus 1 is 2. That should lie on the set S. Right? So therefore 1 plus 1, 2 is there on the set S. Right? Similarly, this 4 plus inverse of 2. Inverse of 2 is, that is 3. Inverse of 2 is, that is 3. 4 plus 3 is, that is 7. Modulo 5 is 2. 2 is also there in S. So like this, actually you try to complete this. So you get this graph, Cayley graph of this Z5 taking this set S is like this. So this Cayley graph, that there are many, properties, and also that to study the spectrum of these Cayley graphs. Many papers are available. I have given some of them as reference, and I think I'll not able to cover all these details. So I'll quickly move to this power graph. Power graph is more interesting because it is a, bit a recent one, and lots of work is, this recently, that work is going on recently. So one may also work on this power graph. Therefore, I'll focus little more on this power graph of a graph because there are many open problems available on this power graph one can work with. So power graph of a group again G is actually, here we are considering that undirected power graph. So its vertex set will be again all the elements of the group, and two vertices U and B means two elements in G are adjacent if and only if any one of these will hold. U to the power m equal to B or B to the power m is U. So for some positive integer m, if one of them can be written as power, some integral power of the other, then they are adjacent. Well, again, I have taken this example that power graph on Z5 we shall consider. On Z5, the vertices are 0, 1, 2, 3, 4, 5, right? So now adjacency is that if you can represent one vertex as power of the other. Here, what is the meaning of u to the power m? Here again, we are taking the operation is addition modulo 5. So u to the power m means you are taking u plus m number of times you are taking. Actually, m terms are there. Okay, so m terms are there. So that is how we perform this addition. So now whether 1 will be adjacent to 2, 1 will be adjacent to, yes, 1 plus 1 is equal to 2 actually. 1 plus 1, oh, I think I have represented 1, 2, 3, 4, 5 kind of thing. Okay, I could have, so yeah, 5 you can take as, I mean, we can take that as a 0 kind of thing. So say 0, 5 you can take as this additive identity. Additive identity will be adjacent to all of them. If you take 1 plus 1 plus 1, 5 times you add. So you'll get that 0 element like this. So you check that you are going to get this to be a complete graph on 5 vertices or K5, this power graph. So this concept of directed power graphs were introduced by Kellerab and Quinn in 2002. They had, defined this directed power graphs, and recently in 2009, Chakraborty et al., they have defined this undirected power graphs, the one that I have given the definition. This definition is given in 2009. So this is a bit recent one. And several work have been done on power graphs. So initially, researchers have started, studying the graph theoretical properties of power graphs, like this connectedness. And then if G is a cyclic group of order 1 or p to the power m, then the graph will be a complete graph. When the graph will be a complete graph? So in the example, the one we have taken, that is a cyclic group of order 5. 5 is a prime number. That is why we are getting a complete graph. Okay, so similarly, what will be the total number of edges in a power graph that has been studied? Then when a power graph will be planar graph, when it will be Hamiltonian graph, all these kind of properties have been studied in the beginning. And then, this is one interesting question that, if we are having two finite groups, G1 and G2, then if G1 and G2 are two, isomorphic groups, if these two groups are isomorphic, two groups are isomorphic, then obviously those graphs, power graphs we get will also be isomorphic. But the converse is be difficult. What will be the converse problem? If the power graphs of two groups are isomorphic, then the question is that whether the corresponding groups will also be isomorphic. So this question has been answered partially by P.J. Cameron and Ghosh, and they have concluded that in case of infinite commutative group, this answer will not be true. However, for finite commutative group, they have proved that this is correct. This answer will be yes. That means whenever the power graphs are isomorphic, corresponding groups are also isomorphic. And later on, people have also done, several research on this same question to answer this question, that several research papers. So it is, already time, I think. So I will not, all these references I have given, you can go through. So on these power graphs, however, that spectrum was not studied till that 2014. In 2014 only, that Chattopadhyay and myself, Chattopadhyay and Panigrai, Chattopadhyay, my student actually, Sripanna Chattopadhyay, that she also studied some properties, and in 2015 that we started studying the spectrum of, this one, Laplacian spectrum of this power graphs. And we have also connected the link with, the relation between power graphs and Cayley graphs of some groups. And that again, Chattopadhyay has done a lot of work on these power graphs. The spectrum of power graphs, Laplacian spectrum, adjacency spectrum. So all those references I have given. So just this is finally just I'll give, briefly I'll just discuss about that, some graphs associated with rings. So there are several graphs again associated with a ring. So the most popular one is again the zero divisor graph, and commuting graphs, non-commuting graphs are there. So this zero divisor graph is also very interesting one. So zero divisor graph on a commutative ring with unity is that the vertex set will be consist of the here that, and let me go to the definition. So the zero divisor graph gamma r on this ring R is a graph and whose vertex set is the set of all non-zero zero divisors. You know the definition of zero divisors, so I am not explaining. So the set of all non-zero zero divisors will be taken as vertex set, and two of them will be adjacent if their product is equal to 0. So here I have given one example of zero divisor graph on Z15. So on Z15, what are all the zero divisors? All the zero divisors on Z15 are 3, 5, 6, 9, 10, and 12. We can see they are the zero divisors in Z15. You check, and that the zero divisor graph will be like this. In fact, this is a complete bipartite graph. In one part, 5 and 10 are there. On the other part, 3, 6, 9, and 12 are there. And see, 5 is adjacent to all the vertices on the other part. Here, 10 is also adjacent to all the vertices on the other part. In fact, this is a complete bipartite graph. One can verify that the zero divisor graph on Z15 looks like this. So then this zero divisor graph, the definition I have given, this was due to Anderson and Livingston actually. On Anderson and Livingston in 1999, they have given the definition and they have studied some properties of zero divisor of graph. And after that, many other researchers have worked on these properties of zero divisor graphs. They have investigated. And again, this Chattopadhyay, Chattopadhyay and others, they have started, studying this spectrum of zero divisor graphs. They have studied Laplacian spectrum of zero divisor graphs. And after that, some other researchers have also studied that of Kami et al. They have explored signless Laplacian and normalized Laplacian spectrum of zero divisor graph. And most recently, actually, that in 2021, that Bajaj and me, that my another student, Saraswati Bajaj, and myself, we have worked on this adjacency spectrum of zero divisor graph on the ring Zn. And in 2022 itself, actually very recently, that we have studied universal adjacency spectrum of zero divisor graph on Zn. So these two papers have been published actually, that I have given references, and you can see. I hope it is already time. So these are the references that here. The first reference you see, this is kind of survey paper on this power graphs. One can see to have this paper to learn more results on power graphs. And then this Anderson, Livingston, the definition of zero divisor graph they have defined here. They had published in Journal of Algebra. Then Saraswati Bajaj and me, we have published this adjacency spectrum of zero divisor graph of Zn in Journal of Algebra and its applications in 2021. And then recently, that Saraswati Bajaj and myself, we have published this paper on that universal adjacency spectrum of zero divisor graph on this AKC International Journal of Graphs and Combinatorics. If you like, you can go through. And there are, this is the important paper of P.J. Kamarian and Ghosh. They published in Discrete Mathematics to discuss about that isomorphic problems. And then papers on power graphs. You can see Chattopadhyay, Sriparna Chattopadhyay, and myself. There are several references I have given. and you can, if you like, you can have a look. And this is the paper that Hammers and Omidi, the linear algebra in its application, they had given the definition of universal adjacency matrix in 2011. And I mean, some more references are there. I think it is already time, and thank you for your attention. If I'll happy to answer your queries if you have any. So please. So that's all my presentation. Am I audible to you?
Yes, madam, you are audible.
Okay. So if any question, any query,
Participant, do you have anything to ask to the madam? Madam is quite ready to answer your questions. Or if else, you can post your questions to the chat box.
this was the paper by Chakraborty and Ghosh. There, where they have introduced the power graphs, concept of power graphs in 2009.
Madam, there is a question.
Yeah, sure.
Mr. Satyavlu Srinivas.
Yeah.
Rao,
Yeah.
that did you use computer program for your work?
No, not at all. No computer work. Fully theoretical. Any other question?
Shweta, can I ask a question? Shweta?
As you took time out of your busy schedule. Sorry, madam. You can ask the question, madam. Annapurna, madam, can you hear me? You can ask the question, madam.
Yeah. Just to have the madam.
Yeah.
I just want
Yes.
madam.
Yeah,
Yeah,
sure.
can we associate the graph for any group? Like, is there an association between groups and graphs?
Yeah. Other way around is also there. With graph also, people are, associating groups actually. So there are, several concepts is there. I have seen in my department, two of my colleagues are there. They are working in that direction. They are associating.
Pardon?
Graphs actually, but I don't work in that direction. Okay.
Yeah, in the day, just
They are,
if you have an idea, because you are
people.
working.
Mainly they are algebra people, and they associate groups with graphs.
Yeah, associate, given any group, by whatever may be the group, a Euclidean group or cyclic group or metacyclic group, whatever may be the group, can we associate, my question is a graph. Similarly, given a graph, can we associate a group corresponding to that group?
They are doing. See, one is the automorphism group is there always actually associated with a graph. Automorphism group is always one can have. Besides this, besides this, there are some other kind of groups also. I mean, very active research is going on in that direction. Two of my colleagues in my department, they are working actually in that. Yeah.
Because in my thesis, I have several types of groups. As I said, my thesis is on projective geometry and projective planes. I get so many groups, different types of groups, automorphism groups, non-cyclic groups, so several groups. But I have a feeling that my groups can generate some kind of graph. I have the feeling, but I'm not able to pinpoint it. So
no,
for that time,
you can generate also graphs. I think you can generate by now. Taking any group that the power graph we have generated, you can always have a power graph out of your group. Those groups you can have.
As I understand, there are so many groups associated with power graphs, universal graphs you have explained. So that means there is a relation. Every group can generate a graph, and every graph can generate a group.
So people are looking into, in fact, that originally directed graphs were associated with groups. That was in the beginning actually. Later on, people are looking into the undirected graph.
Okay. Thank you so much. Thank you.
Yeah, welcome.
I am very grateful, madam, as you took the time out of your busy schedule.
Thank you.
Please accept our thanks for a great presentation, madam.
Yes, sure, madam. Thank you.
Now I call upon Monica to propose formal vote of thanks. Before that, there's a certificate of appreciation for you, madam.
Okay, sure. Thank you.
Please just stop sharing, madam. If you stop share, then we can share the certificate.
Okay, I have done.
Madam, please accept our appreciation certificate for you, madam.
Thank you, madam.
Well,
yes, good afternoon, one and all. It gives me an immense pleasure to propose vote of thanks of today's session on the behalf of Department of Mathematics and Statistics, RVVR Women's College.
You properly. Your voice is breaking.
Okay. Ma'am, is it audible now?
Yes, you are audible now.
It gives me an immense pleasure to propose vote of thanks of today's session on the behalf of Department of Mathematics and Statistics, RVVR Women's College. At the outset, I thank today's resource person, Professor Pratima Panigrahi ma'am, for accepting our invitation and enlightening us about graph theory, which is an active area of mathematical research, and giving deep insights into the topics, Cayley graphs of groups, power graphs, zero divisors graphs, etc. Now, I would like to thank our Honorable Secretary, HMPS, Professor K. Mutyam Reddy sir, and our Secretary cum Correspondent, Professor Sudarshan Reddy sir, for their continuous support in organizing the faculty development program. Now, I would like to thank our principal, Dr. J. Achutadevi ma'am, for her constant support. A special thanks to Shweta ma'am, Head Department of Mathematics, RBY Women's College for organizing the event. Finally, I would like to thank all the participants for patient hearing and making the session successful. Thank you, one and all.
Thank you, Monica. Thank you, each and everyone, especially Pratima Madam, for accepting our invite in spite of your busy schedule, Madam.
Yeah, thank you, madam, for inviting me also. Yeah, this is, although
We are
I am
quite
very
lucky enough, Madam, to hear your speech, Madam.
Yeah, thank you. Actually, yeah, although I'm very busy and our classes are going on now, no, and semester overlapping also held last month. Yeah. So actually, this is basically women's college, and I thought that it is my duty to, deliver lectures so that more women mathematicians will be enlightened, and in future also we may get actually some more, women mathematicians. That is why I thought that, I must accept this invitation. Thank you.
Thank you.
Yeah.
Dear participants, tomorrow's session will be by Professor Rukmini Devi Madam on minimal and maximal surfaces, some common properties at 3 o'clock. Please do join at 3 o'clock tomorrow for the next session. Thank you each and everyone for patiently hearing.
Thank you, madam. Then I am leaving. Thank you so much.
Thank you, madam.
Okay.
Thanks.
Thank you. Okay. Bye, everybody. Have a nice day.